Let's do another example where we calculate the relative abundance of isotopes. In this example, we're going to use bromine, which exists naturally as two different isotopes. The lighter isotope, bromine 79, has an exact mass of 78.92 AMUs. Okay, I'm just rounding to the hundredths place there. The heavier isotope, bromine 81, has a mass of 80.92 atomic mass units. The average atomic mass of bromine is, what is it? Well, we need to look it up on the periodic table. So let's find the average atomic mass of bromine. Here it is on the periodic table, and we can see that the top number on the periodic table is 79.904. So I need to look that number up on the table to kind of fill in the missing piece of information in this question here. So 79, I'm going to round to the hundredths place, 0.90 atomic mass units is going to be the average atomic mass of bromine. Given that information, let's calculate the relative abundance of each of the bromine isotopes, bromine 79 and bromine 81. So we need to take an approach where we set up an equation that's like the weighted average. If we were calculating how we got the 79.90 weighted average, that is going to be the average of the mass of each element, so 78.92, the light isotope mass, multiplied by its relative abundance. So I'm just going to call, I don't know what that is. That's what I'm trying to calculate. So I'm just going to call that X. And then I need to also take the heavier isotope's mass, 80.92 atomic mass units, and multiply it by its relative abundance. I don't know what that is either, so I'm just going to call that Y. So I have two unknowns here, X and Y, that I need to calculate because I need to figure out the relative abundance of each of those bromine isotopes. Uh-oh, two unknowns means that I need two equations, right? I can't solve it unless I have two equations. So what else do we know about X and Y? Is there any other quantitative relationship that I can figure out for them? Well, I know that bromine exists naturally just as those two isotopes. So those two relative abundances need to add up to 100%, right? Another way of saying that is that X and Y as decimals would need to add up to 1 because the relative abundances of those two bromine isotopes need to add up to 100%. So now I have two equations. And if I have two equations and two unknowns, then that is something I can solve. I am going to rearrange this equation to say that y equals 1 minus x. And then I am going to take this value and plug it in for y. And that will enable me to solve for x. And once I solve for x, I can solve for y too. So I'm going to substitute in that value for y, and then I'm going to solve. I'm going to leave out the AMUs to say that 79.90 equals 78.92x plus 80.92 times 1 minus x. Because remember, I plugged in this value for y up here. Okay, now I can easily use this relationship to solve for x. So 79.90 equals 78.92x. Then I need to distribute the 80.92 minus 80.92x. If you collect all the terms on each side, you can solve for x, and you'll find that x equals 0.51, or 51%. Solving for y, we know that y equals 1 minus x, so that's going to give me 0.49, or 49%. Now, which is which? Well, X, going back to the original equation, X is going to be the mass of the lighter isotope, and Y is the mass of the heavier isotope. So we just figured out that 51% of bromine is going to be the heavier isotope, 81 Br, and 49% of bromine is going to be the lighter isotope, 79 Br. So these two isotopes of bromine exist in almost equal, 51% and 49% relative abundance. Oh wait, I think I switched those by accident. So X was the lighter isotope. Yeah, X is the lighter isotope. So 79 bromine is going to be 51%. And the 81 bromine is going to be the heavier isotope. And the way that we figured that out is just that X is the variable that I had associated with the lighter mass, and Y was the variable that I had associated with the heavier mass. So the lighter isotope is 51% and the heavier isotope is 49%. Phew, that's